The study of the universe's origins and expansion is at a critical point, with cosmology facing some of its most fundamental questions. One of the primary concerns involves understanding the speed at which the universe is expanding. For more than a decade, two primary methods of measuring this expansion rate have yielded conflicting results. Observations made from the current state of the universe suggest that the rate of expansion, referred to as the Hubble constant, is about 9% higher than what the predictions based on early universe data suggest. Scientists had hoped the James Webb Space Telescope, JWST, the most advanced telescope ever constructed, would help resolve this issue definitively. However, the telescope's groundbreaking new data has instead strengthened the discrepancy, raising questions about the accuracy of the established cosmological model. This development has led to serious debates about whether new physics might be required, either to modify or completely replace the existing theories that have been in place for over 40 years. It's an exciting possibility that we might be missing an essential component of the universe, which could significantly alter our understanding. The universe's beginning traces back to the Big Bang, a massive explosion that created energy, matter, and space nearly instantaneously. Following this, the cosmos began as a hot, dense plasma, a mixture of matter and antimatter particles. These particles collided and annihilated each other, but scientists believe that some unknown imbalance allowed slightly more matter to form than antimatter, preventing the universe from destroying itself. Gravity then condensed the plasma, raising its temperature to the point where sound waves, known as baryon acoustic oscillations, traveled through the plasma at more than half the speed of light. Meanwhile, the early universe's dense energy content stretched spacetime itself, pushing a portion of matter far enough from the intense heat to survive. As the universe expanded, like a balloon inflating, the story commonly told is that regular matter began to clump around invisible dark matter, eventually forming the first galaxies. These galaxies are thought to be connected by a vast cosmic web, linking them through dark matter and energy. As the universe continued to expand, its energy density and expansion rate gradually decreased. However, roughly 5 billion years ago, galaxies began receding from each other at an accelerated rate, a phenomenon driven by the mysterious force called dark energy. The most widely accepted explanation for dark energy is that it acts as a constant force in space and time, woven into the expanding fabric of spacetime. Named lambda by Einstein in his theory of general relativity, dark energy's density remains unchanged as the universe grows, while the density of regular matter decreases. Over time, dark energy became the dominant force driving the expansion of the universe. Along with dark matter and regular matter, these forces are part of the lambda cold dark matter, LCDM, model, which describes the evolution of the universe and predicts its eventual fate, heat death, also known as the Big Freeze. While many of this model's predictions have been confirmed, the question of dark energy and dark matter remains unresolved. One of the most significant issues facing cosmologists is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. This discrepancy is so large that it has become one of the most pressing problems in cosmology. Measurements based on observations of the early universe suggest a faster rate of expansion than predicted by the LCDM model. These early measurements have been thoroughly tested and validated through a variety of observations. As Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest James Webb Space Telescope measurements, stated, "The only explanation for the disparity is that our current model is missing something important. To measure the expansion rate of the universe, more than just a simple observation is required." One of the primary techniques for this is examining the cosmic microwave background, CMB. The universe's first light, emitted about 380,000 years after the Big Bang. This imprint is visible throughout the entire sky and has been mapped extensively to calculate the Hubble constant. Between 2009 and 2013, the European Space Agency's Planck satellite provided a detailed map of the CMB. This map shows the universe as nearly uniform, but slight temperature variations mark areas with higher or lower matter density. These variations reflect the imprint left by baryon acoustic oscillations and helped cosmologists calculate the Hubble constant, which came out to around 67 kilometers per second per megaparsec. To clarify, this means that a galaxy 1 megaparsec away would recede at 67 kilometers per second, and at a distance of 20 megaparsecs, the recession speed would rise to 1,340 kilometers per second. If a galaxy were farther than 4,175 megaparsecs, it would be receding faster than the speed of light. Another method for determining the expansion rate involves studying Cepheid variables, pulsating stars whose outer layers expand and contract in a regular pattern as they absorb and release radiation. This behavior, discovered in 1912 by astronomer Henrietta Swan-Leavitt, allows astronomers to measure the star's absolute brightness, which can then be used to estimate their distances. The Cepheid method, known as the cosmic distance ladder, has been a groundbreaking tool for measuring vast cosmic distances. The first step in this ladder involves measuring nearby Cepheids and cross-checking their distances. Afterward, astronomers can measure the distances of more distant stars and supernovae by observing their redshift. By comparing these measurements, they can calculate the Hubble constant. In 2019, Rees and his team used this method by targeting the Milky Way's nearest neighbor, the Large Magellanic Cloud. Their findings were startling, showing a much higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck data. While the Hubble Space Telescope was able to make significant contributions, its precision was limited in crowded regions of space, causing distant Cepheids to blur with neighboring stars. Some cosmologists suggested that this discrepancy could be due to a measurement error. However, when the James Webb Space Telescope launched in December 2021, expectations were high that it could resolve or perhaps confirm this discrepancy. With its 6.5-meter-wide mirror, nearly 3 times the size of Hubble's, and its superior infrared capabilities, JWST could observe fainter objects and detect a wider range of wavelengths. Study. Comparing Cepheids in the galaxy NGC 4258 to supernovae revealed results nearly identical to Rees's previous findings, around 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing, returned similar values, 69.6 kilometers per second and 66.6 kilometers per second per megaparsec, respectively. These findings have caused a stir in the cosmology community. As explained by cosmologist Ronan Kai from the University of California, Merced, even a small difference of just 7 kilometers per second is highly unlikely to be a random error, especially given the precision of the measurements. This has led to a division among cosmologists, with some suggesting measurement errors, others proposing new physics, or a combination of both. Kai believes that much of the data points toward the need for new physics. One leading hypothesis is that dark energy's behavior has evolved over time. If dark energy was once stronger and gradually weakened, it could have made the universe appear smaller in its early stages, resulting in a faster expansion rate today. Other theories suggest the existence of 2 types of dark energy or interactions between dark matter and light, but these ideas come with complexities that many cosmologists are reluctant to accept without more evidence. The discoveries made by the James Webb Space Telescope are not only challenging our understanding of dark energy and dark matter, but also reshaping our views on galaxy formation. By observing galaxies further back in time than ever before, JWST has uncovered galaxies much more massive and developed than expected, forming just 300 million years after the Big Bang. These early galaxies, which were thought to consist mostly of young, hot stars, were found to contain heavy elements and even supermassive black holes at their cores. These features challenged the traditional model of galaxy evolution, suggesting that galaxy formation processes may have been faster and more efficient than previously thought. Furthermore, these findings deepen the mystery of dark matter and dark energy, both of which remain poorly understood despite being dominant components of the universe. Dark matter, which interacts only gravitationally, still eludes precise detection, prompting ongoing research. Similarly, dark energy, which is responsible for accelerating the expansion of the universe, presents discrepancies like the Hubble tension, raising the possibility that its properties may not be constant across spacetime. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate at different stages of the universe's history. To solve these mysteries, astronomers will need both advanced observational tools, like the James Webb Space Telescope, and theoretical frameworks that can incorporate new data without discarding the successes of current models. The implications of JWST's discoveries extend far beyond cosmology, touching broader astrophysical questions, including the origins of life and the conditions necessary for life on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets might form around other stars, offering insights into the prevalence and diversity of life across the cosmos. Looking ahead, the James Webb Space Telescope promises to push the boundaries of our understanding of the universe. Its unprecedented sensitivity and resolution will allow astronomers to study the atmospheres of exoplanets, map galaxies in greater detail, and examine the earliest moments of cosmic history with unparalleled precision. JWST's ongoing mission is set to continue revolutionizing our comprehension of physics, astronomy, and our place in the cosmos. Whether uncovering the mysteries of dark matter and dark energy, understanding galaxy formation, or searching for life beyond Earth, the telescope is poised to transform our view of the universe in ways once thought impossible. In conclusion, the intersection of cutting-edge technology, theoretical innovation, and precise observation heralds a new era for cosmology and astrophysics. JWST's contributions will refine our understanding of the universe's origins, challenge established theories, and open doors to groundbreaking discoveries as we continue our journey of exploration. The universe's mysteries await, and with JWST leading the way, we are poised to uncover the secrets of our cosmic heritage and future. The James Webb Space Telescope, JWST, offers more than just precise measurements of the universe's expansion and detailed observations of early galaxies. It is positioned to tackle some of cosmology's deepest questions. While the notion that our understanding of the universe could be fundamentally flawed is not new, JWST's precision has sharpened this possibility. Central to the universe's structure are dark matter and dark energy, which are still not well understood. JWST's ability to study the early universe and observe galaxies that formed just 300 million years after the Big Bang has provided unprecedented insights into galaxy formation. These observations challenge the established theory that galaxies should have taken longer to form, suggesting that processes like star formation and black hole growth may have been more efficient in the early universe. Moreover, JWST's observations are helping to advance the study of dark matter. This elusive substance is believed to have played a crucial role in shaping the universe's structure by exerting gravitational forces, but its exact properties remain unknown. JWST's insights could help us understand how dark matter influenced galaxy formation and possibly reveal new characteristics of this mysterious substance. Beyond dark matter, JWST is also assisting in the study of exoplanets and the conditions that might allow life to thrive on other worlds. One of the telescope's main objectives is to analyze exoplanet atmospheres, looking for signs of habitability or even life. By investigating the chemical makeup of these atmospheres, scientists hope to determine the conditions that might support life elsewhere in the universe, offering insights into how common Earth-like environments may be. As JWST continues to analyze the data, it becomes increasingly clear that we are on the brink of discovering new physics. Whether it's unraveling the nature of dark energy, exploring the unexpected complexity of early galaxies, or examining the behavior of dark matter, JWST is opening up new avenues for understanding the universe. The telescope is not just refining our current theories. It is challenging them, urging scientists to rethink fundamental assumptions and explore new possibilities. These discoveries are pushing the boundaries of physics, astronomy, and even philosophy, as we deepen our understanding of the laws that govern our reality. As we continue to study the universe through JWST's lens, we are not just learning about distant stars and galaxies. We are gaining profound insights into the very nature of the cosmos. The questions raised by JWST's findings could lead to a paradigm shift in how we understand the origin, structure, and future of the universe. As we continue to explore the cosmos through the lens of the James Webb Space Telescope, JWST, the potential for a paradigm shift in our understanding of the universe grows increasingly likely. The telescope's unprecedented capabilities have already provided a wealth of data that challenges many of our long-held assumptions about the cosmos. For instance, the detection of early massive galaxies, forming just 300 million years after the Big Bang, raises significant questions about the timescale and processes involved in galaxy formation. These galaxies appear far more mature than the models predicted, suggesting that certain processes like star formation and black hole growth may have occurred much faster and more efficiently than we had imagined. This discovery has spurred intense discussions in the scientific community about whether our current models for the evolution of galaxies and cosmic structures need to be revised. Moreover, JWST's study of the early universe has revealed further complexities in the interaction between matter, and dark energy. The telescope's infrared capabilities allow it to look deeper into the cosmos, examining objects and events that occurred in the first few hundred million years after the Big Bang, a period that was previously beyond our observational reach. These observations are crucial for understanding the role of dark matter, which, despite making up about 25% of the universe's mass, remains one of the most elusive components of the cosmos. While dark matter doesn't emit light and can only be detected through its gravitational effects, JWST's precision may help illuminate how dark matter contributed to the formation of galaxies and large-scale cosmic structures. This is a critical step in understanding how our universe took shape and how it continues to evolve. In addition to the ongoing quest to understand the fundamental components of the universe, dark matter, dark energy, and galaxy formation, JWST's observations are also offering exciting new possibilities in the search for life beyond Earth. One of the telescope's key missions is to study the atmospheres of exoplanets, searching for signs of habitability. By analyzing the chemical composition of these exoplanets' atmospheres, scientists hope to detect the presence of molecules like oxygen, methane, and carbon dioxide, which are potential indicators of life. JWST's ability to observe exoplanets in greater detail and with higher sensitivity than ever before could bring us closer to answering the profound question: are we alone in the universe? JWST's contribution to this field extends beyond merely identifying potentially habitable exoplanets. It also promises to help us understand the environmental conditions that might support life. This includes studying the climate and atmospheric conditions of distant planets and learning how these factors might influence the potential for life to emerge. By investigating the chemical interactions that occur within these exoplanetary atmospheres, scientists hope to uncover new insights into the processes that govern planetary habitability, insights that could have profound implications for the search for life beyond Earth.